Welcome back to AI for Mechanical Engineers. Today we're going to learn neural networks. And for the first section, we're going to talk about perceptrons. Perceptrons is a model that do binary linear classification. So here, this is one representative example of a perceptron model. And a perceptron model is composed of input features and bias and also weights here. This 1, 3, minus 2, these are all some weights. And we're going to do some summation here. And this is a step function, which can produce a result for classification. So let's see how this perceptron model works to do some classification. For example, I told you that here this x1 and x2 are input features, and this 1 is a bias. And these are weights, and what we do here is we do a sum of the multiplication of the weights and the input features and biases. So what happens here is we multiply 1 times 1, and then sum 3 times x1, and also add the multiplication of minus 2 and x2. Then, after doing the sum, this information passes the sine function. This is a sine function, which could be some function like the step function here. Like this is minus 1 if it's negative and 1 if it's positive. Or you can also set this function as some function as 0 and 1. So it's a binary function. So however, now if some information passes through here, and for example, let's say that if this is positive, then we're going to get some positive value. And if this is negative here, then we're going to get minus 1 or 0 here. So this one, y, will be the result of our class, 0 or 1. So we can do some binary classification. If we write this process into an equation, we can write it like this one. Y hat, where this is y hat, equals to g. This is our sine function. And here, this is our bias. W0 is our bias. The weight connected to our bias. So here, it's simply 1. And x transpose is our input features. So here we get x1 and x2 transpose. And w here is the weight vector. So 3 and minus 2 here is multiplied here. So here, this will be a function that does binary classification. So if we have our function as this one, y hat equals to g, 1 plus 3x1 minus 2x2 from this perceptron model, we can draw this line here, this one, which corresponds to 1 plus 3x1 minus 2x2 equals to 0. And depending on which side that the data exists, some part will be negative and the other part will be positive. So by using this fact, what we can do is, for example, we can do binary linear classification. And as an example, let's try to see the class of this data point, minus 1, comma 2. So we're going to substitute minus 1 into x1 and 2 into x2. So we're going to have this equation here, minus 1 for x1 and minus 2 for x2. And if we calculate this, we're going to get minus 6. And if we're using our step function, something like this one, if it's negative, it's minus 1, and if it's positive, it's 1, then we're going to get minus 1. So this part will be the negative part. So therefore, what we can know here is this part is for the negative class, and this part is for the positive class. So therefore, this line that we design using our perception model here, using these weights, becomes a linear classifier because it acts as a classification boundary. And this linear classifier can be expressed with our three weights, W0, W1, and W2. Here, W0, W1, and W2, where X1 and X2 are our input features. So this is how we can do binary linear classification in a 2D space. And we can also do this binary linear classification in a higher dimensional space. And how can we do this? We can do this by adding more neurons. Like this model here. This is also a perception model, but with more input features. So what this means is, for example, here we have the input features from x1 to xm. So we have m input features. And therefore, we also have more weights here. And then, what this means is, if we are trying to calculate y hat, we first need to calculate this one. And of course, we need to do some, we need to apply some function here to determine the class. Something like this step function, or the sign function here, like -1 to 1. However, the important thing here is that we have more and more features here. And what this means is we can have some classification boundary in a higher dimensional space. And for example, let's think about one case. That we have 3 input features. Then this will be just simply a plane in a 3-dimensional space. So now here, this becomes our classification boundary. So this is our new classifier in a 3-dimensional space. So if we want to do a classification problem in a higher dimensional space, the only thing that we need to do is to add more neurons here if we're using a simple perception model. Now, let's move on to multi-layer perception models. So to talk about multi-layer perception models, we first need to understand why we need multi-layer perception models. Even these perception models could also do some good jobs in linear classification. So let's first talk about this XOR problem. So XOR problem, this XOR means exclusively OR. And let's see what it means here more in detail in this picture here. So let's say that these red dots belongs to class 0. And these green dots belongs to class 1. So the coordinate here is 0, 0, this is 1, 0, 0, 1, and 1, 1. And if you see this table here, we have x1 and x2. So we have this coordinate space x1, x2. And if it's 0 and 0, then this is class 0. And if it's 0 and 1 here, then it's 1. So 0, 1 is class 1. And if it's 1, 0, it belongs to class 1. And if it's 1, 1, it belongs to class 0. So it belongs to class 0 only if these x1 and x2 are the same value. So here, however, let's say that we want to do some classification in this problem here. And let's try to imagine how can we do this. And actually, there's no way to do this using a single classification boundary. For example, if we draw some line like this one, we can't correctly classify our green class and our red class because here. This green class will belong to the same class to these red class. So therefore, what we need to do is we need to actually add one more line, something like this one, and make some boundary, classification boundary like this one. So in this XOR problem, the problem is we can't classify with a single linear classifier. This is because a single neuron indicates we have one linear classification boundary, and this single neuron is for our alpha neuron. However, in practice, we are dealing with very complicated lines, like a nonlinear curve. And to do this, we can imagine doing some approximation of these nonlinear curves using multiple lines. So for example, if we have these data and if we're doing some regression, we want to achieve this nice curve, and we can think this as some kind of a composition of multiple linear lines. And also here, for example, if we're doing classification, and we can see that we are going to need to have some nonlinear classification boundary that could be expressed with multiple lines like this one. And in these cases, which occurs frequently in practice, we need to have multiple classification boundaries, or we need to somehow create a very good model that can approximate these nonlinear curves. And we can do this by using multilayer perceptrons. So to explain this in more detail, let's go back to our XOR problem. And I told you that we need to have at least two lines to create a proper classification boundary in this problem. And to create these multiple lines, I told you that we can use multi-layer perceptron, which is called as MLP. And this is also known as artificial neural network, which is the most basic version of the neural network models. And in multi-layer perceptrons, we have multi-neurons, which indicates multiple linear classification boundaries, or it can also be some nonlinear and also a boundary for regression problems. So since we were talking about XOR problem, which had two features, X1 and X2, let's think about these two independent perceptrons here. So we can think that this first perception model will create one classification boundary. I'll call this as one line. And what if we add one more perception model? This will also create one line for classification. And if we merge these two models into one, we're going to get this kind of model. Here, all of the weights are connected. So you can see that these were for the first perception model here, and these weights are for the second perception models here. And this perception model will be able to create two lines for our classification boundaries. So let's start with this MLP model that we just talked right in the previous slide here. So this is a model that is called multi-layer perceptron, MLP. And what we also need to do here is we need to add, or we need to change our activation functions. These were some step functions before, something like this one, -1 to 1 or 0 to 1. However, the problem here is that we're going to talk more about the details in the later slides. However, we need to calculate some gradients of our loss, which is the error function. And during this procedure, we need to calculate the derivatives of our functions. However, this function, this step function, is not really good to calculate the derivatives, because you can see that this is discontinuous here, and also the derivative here are all 0. So it's not a really good function to use when we're training neural networks. So what people thought is that we can change this activation function to a nonlinear activation function. For example, something like this sigmoid function, which has this kind of a curve here, and this can be expressed as 1 over 1 plus exponential minus x here. So here, now we changed our step function to some other differentiable nonlinear activation function. And we're going to talk more about the details why we need these differentiable activation functions in the later slides. So there are two ways of looking at our artificial neural networks. So when we talk about this model here, we can see that there are some circles here, which we call these as neurons, and some lines that connects these circles, which are called as weights. The first way to see our neural network model or an MLP model is to see these as some layers of weights. And the second way to see our neural network or MLP is to see this as layers of neurons. And these two perspectives are both also important because if we see our neural network or MLP as layers of weights, we are seeing this with more emphasis on our trainable parameters, which we train our weights and biases. For layers of neurons, these are also important because this is how our information is transformed and transported to one layer to another layer. So here, these are inputs and outputs of a function, and these contains the information that we want to know. And I would like to introduce one another perspective of looking into our artificial neural network, and this is looking as a kernel learning. So let's take a look into this example of doing a nonlinear classification. So we can see these data points, for example, these green data points and these red data points, which indicate different classes. And if we're doing some classification on these data points in two-dimensional space, it's impossible to do this with a linear classification boundary. We need some nonlinear classification boundary here. And for example, if we look into this video here, we have a similar data points here. So here, these are some blue data points, and the surrounding data points are red. Here. And we can see that this cannot be separated in two-dimensional space. We can't draw a single line that can do this classification. However, if we transform these data points into another space, for example, using some kernels from SVM or some MLP, we can create this another space in a three-dimensional space here. It was 2D, and we transform this into 3D. And then what we can do is we can draw a plane that's gonna divide or separate our blue class and our red class data points. So we can also think as artificial neural networks or MLPs as doing some kernel learning to transform our data points into another expression, and therefore in that expression we can do classification better or doing regression better. So let's get back to our XOR problem, and let's think about how can we do this using MLPs. So as we taught this in the previous slides, we know that this is not linearly separable. We need multiple lines. And however, one way to think of this is to add more neurons using perceptrons, so we can have multiple lines doing this. And another way to think this is to do some nonlinear mapping. So for example, let's try to do a similar thing that we have done in our video. We changed our data points to a 2D data expression to a three-dimensional space, and we saw that we can do some classification in that space. So for example, let's try to do a similar thing here. So what we're going to do is we're going to try to make this 2D data to 3D by this function, phi. So we changed our two-dimensional space, which was expressed with xu and xv, to xu, xv, and xu times xv here. So 0, 0, this is 0, 0, and if we multiply 0, 0, it will be 0. If we multiply 0 and 1, it will be still 0. If we multiply 1 and 0, it will be still 0. And the most important part happens here. So originally, we had one point here, and this was 1, 1, and it becomes xu, xv. The last dimension becomes 1 here. So this now became a three-dimensional space, and in this three-dimensional space, we can do linear classification with this single plane. So we have one linear classification boundary to solve this XOR problem. So let's also talk about this more in detail with the schematics of our neurons and weights. So when we first did our EXO problem, we started with some very simple perception model. And let's start with this one. These simple neurons connected to these weights. And if we see these neurons, there's a single neuron. And using these two input features, we know that we cannot make our classification boundary so the data points can be linearly separable for our XOR problem. So if we just use this one, we can't do our XOR problem, classification problem, properly. So we need to think that we need to add some kernels and neurons. So we're going to connect some kernel function to our neurons here. One for bias, x1 and x2 for our input features, and we have this phi as our kernels. And what happens here is we're going to make our kernel to represent x1, x2, and x1 and x2 here. Then what happened here was this was not linearly separable. However, we saw that if we transform our space using x1, x2, and x1, x2, now this one becomes linearly separable. And therefore, here, if we are able to learn the weights here properly, then we can do some linear classification. And one good news is that this kernel, phi, we can also replace this to another neurons, because these nonlinear mapping can be represented by another neurons. For example, if we add more layers between our input features and biases to the final features here, we can add more layers. It could be a single layer, or it could be multiple layers here. Then these neurons, these layers of neurons or layers of weights, acts or works as kernel. So then we have our input layer. We have some additional layers. Which we call these as hidden layers. And these will act as kernel. And we have some, these are the final features. And we're going to have our output here. then we're going to be able to do our classification or regression with some better feature. So it will make us to make our model to learn a data much better. And we can see these additional layers or hidden layers as some nonlinear kernels if we use nonlinear activation functions, such as the sigmoid function that we learned before. We're going to talk more about the different types of nonlinear activation functions in the later slides. Now, let's try to understand what happens inside our MLP and how this enables us to learn some nonlinear classification boundary. So let's first look into this nonlinearly distributed data here. So for example, let's try to use this neural network here. So here, these ones are our biases, and we have our input feature, and we have an additional feature in the middle, Z1, Z2, and let's say that this Y1 and Y2 are the outputs. And to make this more simple, for more simplified schematic for our MLP, let's just omit our bias because these are something that are included yearly in all of our layers. So we're going to now omit drawing our bias units. So we have a much more simplified version of our MLP here, and we know that these neurons and weights are connected to each other. So using this MLP, let's try to understand what happens in this layer and what happens in this layer. So we can see that these features are x1 and x2 here. So x1 goes inside here and x2 goes inside here. And these information of x1 and x2 is passed through these weights. And then it is transported to the next layer as z1 and z2 by some nonlinear function. And let's see what happens inside z1 and z2. And if we visualize z1 and z2, for example, of this one, we can see that here. Now, the red dots and blue dots seems to be linearly separable. For example, if we draw one line like this one, I think that this could be classified with some good performance here. So this means that by transforming our input features using some layer of weights, we made some input features that were not linearly separable to features of Z1 and Z2, which are linearly separable. So based on these Z1 and Z2, the only thing that we need to do is find these two weights and do linear classification. That means that we just need to find the weights of that could express this classification boundary in the Z1 and Z2 space. So to summarize, what we're doing with this multi-layer perceptron here, we're trying to transform our input features x1 and x2 to z1 and z2 using MLP, so we can have some linearly separable features. So we can do a very simple linear classification in this space of z1 and z2. If we see this problem in the original X space, the input space, we can see this as doing some piecewise linear classifications using two lines here. So this is something that is similar to what we have learned in our perceptrons. If we're trying to do some approximation of nonlinear curves, we need to have multiple lines. And to have multiple lines for this classification boundaries, we need to add more neurons. And this is what we have done here. For these two X inputs, and if we see that we have two, we can estimate the number of lines that we need to have here. We can add two neurons here. So we have two classification boundaries. So similarly, let's also talk about a different example, which is similar, but let's have some more complexity in the data. Here, now you can see that this is not just a simple two-line problem. And for example, you may think that we need like 4 lines, like these lines here. Then, now what you can guess here is that we need to have 4 neurons to create these 4 classification boundaries. So, yeah, this is just a simple result of visualizing these 4 classification boundaries. And therefore, what we can know here is now we know how to intuitively determine the number of neurons that we may need for doing some classification problem. So if you see in the data and if you think that we need about like 4 lines to do this, you need at least 4 neurons here.